Hello, and welcome back to Shiksha DaCosta. Today we're going to learn about how to turn a quadratic from standard to vertex form by a technique called completing the square. As I mentioned, today we're going to learn how to take a trinomial that's in standard form, ax squared plus bx plus c, and express it in vertex form, which is a times x minus h squared plus k. And the technique to do that is called completing the square. So to start off, I invite you to pause the video here and factor both of these trinomials and then express the area using algebra tiles. Okay, well, if you were stuck with that or if you managed to complete it, great. I'm going to take up the first one at least, and then maybe you can pause when I'm done that to see if you can handle the second. So the first one here, to factor this, I recognize that this is a trinomial where a is equal to 1, so I can employ the sum product rule. To do that, I have to find two factors of 16, which add up to 8. And that's pretty easy. That's 4 and 4. 4 times 4 is 16, and 4 plus 4 is 8. And so this factors into x plus 4 times x plus 4. And to use algebra tiles to describe this, I could draw a rectangle where one of these is the length, one of these is the width, and the area should be represented by this. So if I did that, so that's x plus 4 as the width. X is right there, right? I'm getting that from there, and then the plus 4, obviously. And then for the length, I have this right here, and so that is, again, x plus 4. The rectangle that this creates will kind of look like this. And if I sort of draw these dotted lines along where my known quantities end, I end up with these, but I end up separating my rectangle into several little spaces. And can I confirm that this actually is represented by x squared plus 8x plus 16? Yeah, this square right here is x by x, or in other words, x squared. This square over here is 1 times x, which is just x, and so are these three, right? They are all the exact same size. These ones over here are x times 1, which is just, again, x, and so are these three. And each of these over here is 1 times 1, which is just an area of 1. So all 16 of these have an area of 1. And yeah, that confirms to me that, if the length and the width are both x plus 4, the area is x squared plus 8x tiles plus 8x plus 16. So if you weren't able to do this, pause the video now and factor this, and again try to express it using an area diagram. All right, well, this one's a lot trickier to factor, and I'm not going to go through all the steps here, but suffice it to say that we need to use the technique called decomposition. If you don't know what that is, please feel free to look up one of my videos where I talk about factoring quadratics by that technique, decomposition. Once you're able to factor this into 2x plus 3 times 2x plus 1, I can draw a diagram, an area diagram to model this, and so that would be 2x plus 1, that could be the length, and 2x plus 3, and that could be the width. And the rectangle that I draw, again, I can split that up according to the known quantities. And now I can see that, that's x squared, x squared, x squared, x squared. So there's 4x squared tiles. There's 1, 2, 3, 4, 5, 6, 7, 8 x tiles, and 3 unit tiles at the end. Okay, now that we've been able to successfully show that we can connect algebra tiles to the actual algebraic expression, which of these two would you call a perfect square trinomial? Well, I think quite obviously we're going to go with this one. The algebraic representation, the visual of this is an actual square where the length and the width are exactly equal to each other. And that's really the definition of a square, right? So in this investigation, I'm going to ask you to create a perfect square using algebra tiles. So if I give you one x squared tile, two x tiles, and you can use any number of unit tiles, so in other words, x squared plus 2x plus c, where we don't know how many unit tiles we'll use. If we want this to be a perfect square trinomial, how many unit tiles do we need? How could we arrange these tiles to create a perfect square? What should the value of C be? How many unit tiles should we use? Pause the video here and take as long as you need to draw a diagram that uses exactly this criteria. Well, that's what I got. So I put the x squared tile here. I know that if I am increasing a side length by a certain amount, I have to increase the other side length by that same amount as well. So my two x tiles had to be split up. One went to the length and one went to the width. And that left me with a blank space here, which I could very easily fill in with just one unit tile because I only needed one. I only went up, increased the length and the width by 1 unit each. So this had to be 1 times 1, which is just 1. In other words, in this trinomial, if b is 2, c needs to be 1. And I'll put that over here for safekeeping to look at later because I'm just about to ask you a new version of this question. What if you had 4 x tiles? Could you create a perfect square using those and any number of unit tiles? In other words, x squared plus 4x plus c, what would c have to be to create a perfect square trinomial? Pause the video here and take as long as you need to figure that out. Well, once again, if I am increasing the length by a certain amount, I have to increase the width by the same amount to keep it a perfect square. And I know that I can take an x tile and place it along the length here, which means the other side would be the 1 unit side. So I would increase it by 1. I could increase it by 2 because if I put 2 x tiles here, I can put another 2 x tiles here, which would leave a space open right here that I would have to fill in with unit tiles. Just like so. And so you can see very clearly here that I had to take my x tiles and break them up into 2 groups, one increasing the length and one increasing the width. And each one of them increased the length and width by exactly 2 units. So the area that I was left with having to fill in had an area of 2 times 2, or 4. And so if b is 4, it looks like the value of c also has to be 4 to create a perfect square trinomial. And I'll keep that away for safekeeping as well because I'm about to ask you yet another one. This time without necessarily using algebra tiles, although I am certainly going to show you what it looks like with algebra tiles. What do you think the value of c should be for this to be a perfect square trinomial? Pause the video here and take as long as you need to think about that. Well, for me, I realized that while I was doing the previous few questions, the number of x tiles had to be split into 2, one increasing the length and one increasing the width. Just like this. So if I have 6 x tiles, I increase the length and the width by 3 each, not 6, but 3. And then I ended up with an empty space that was clearly 3 by 3. So the value of c here would have to be 9, right? I took half of b, and that's the length and the width of this empty space, and then length times width, or b over 2, if I square it, I end up with this area right here, which is 9. And I'll keep that over here for later because we're going to do just a couple more. Pause the video here and ask yourself, what does the value of c need to be if b is 8? Well, again, we know that we're going to have that x squared tile, and we have to increase the length and width by half the amount of b, so that's 4 and 4, and that would make this area 16. And I'll keep that aside here for later as well. What about if b is 10? Pause the video here and see if you can figure out, what does c have to be? Well, that is my diagram right here. So I increased the length and the width by half of 10, or 5 each, making this area 5 by 5, or 25. Now that we've gone through this a few times, 5 times in total, Do you notice a pattern happening here? In other words, pause the video and see if you can find out what is the relationship between B and C. Hopefully you were able to see that the relationship is all we always took the B value and we cut it in half. And that gave us the length and the width of this empty space here. So I took B, divided it by 2, and then C, to find the area, I took B over 2, and I squared it. I multiplied it by itself, length times width. And so the value of C seems to always be B over 2 all squared. So in a perfect square quadratic that looks like x squared plus bx plus c, notice this does not have an a value, or the a value is equal to 1. But if you have a situation like this, it's a perfect square quadratic if and only if the value of c is half of b squared. And we're going to use this idea in exploring how to turn a quadratic from standard form to vertex form. So can we convert y equals 2x squared plus 4x plus 6 to vertex form and then use that to find the maximum? Well, in this case, the a value here is 2, and I think I can actually factor that out of all three of these. And one thing to note is in vertex form of a quadratic also has an a value, and both of these are the same in both forms. So the first thing I'm going to do is I'm going to take my quadratic and I'm going to divide it by, sorry, I said 2, I meant -2. I'm going to divide all three of these terms by -2 because that's the greatest common factor. And now I have a trinomial. The problem is this is not a perfect square trinomial. This is x squared minus 2x, so 2 negative x tiles, minus 3, so 3 negative 1 tiles. And if I want to try to make this a perfect square, I'll invite you to go ahead and give this a shot and see what you come up with. Pause the video here and try to make it as close to a perfect square as you possibly can. Well, over here, if I move these two x tiles right over here, then that leaves an empty space here. So this is x minus 1, because I know this side length is x as well, and x times -1 would give me -x. So if this side is -1 and this side also by the same reasoning is -1, then this square would have to be -1 times -1, which is +1. And I actually don't have a +1 to slide in here. Otherwise, I would be able to make it a perfect square, but these -1s just won't cut it. So how can I do that? One way is to explore the idea of zero pairs. So a zero pair is basically saying, let me add and subtract the same number. And by doing so, I haven't really changed the value of this expression. So if I add a zero pair, the value of all of my algebra tiles has not actually changed. But I can use this zero pair now to put this +1 over here and collect all my -1s separately. Just like that. And so the point that I'm trying to make here is that this trinomial, which is not a perfect square trinomial, can be rewritten as x minus 1 times x minus 1, or in other words, x minus 1 squared minus 4. And if that's true, if I can rewrite this as x minus 1 squared minus 4, I'm going to actually do that now. And now I can take this -2 and I can distribute it to these two different terms. So -2 times x minus 1 squared is just -2 times x minus 1 squared. But -2 times -4 is actually +8. And look at that. Doesn't that look like vertex form? That's why this technique is called completing the square, because when we factored out our a value, we had a trinomial. The a value was 1 of that trinomial now, but it isn't necessarily a perfect square trinomial. We can make it one by completing that square. And we just went through an algebraic reasoning on how to do that. We can replace that expression with another expression that has a complete square in it. And once we do that, we can then multiply the a value by both of the terms and realize that once we have it in vertex form, we can clearly see that the maximum is 8. So in a perfect squared quadratic that looks like this, that where the a value is 1, we already talked about that the c value has to be half of b squared. And we can use this idea to actually complete the square. One thing that you may be already able to do is if you had vertex form, you might be able to already expand and simplify these brackets and collect your like terms. And that is a way to turn vertex form into standard form. But today we're going to explore this idea of completing the square, which will allow us to go from standard form back to vertex form. So a quadratic relation that is in standard form can be rewritten in its vertex form by creating a perfect square, and we call that technique completing the square. I'm going to show you how to complete the square, and by doing so, I will be able to find the vertex of y equals 3x squared plus 18x plus 18. And to do that, the first step is to factor the a value out of just the first two terms. And I'll show you exactly where we end up at the end of this. But here are all this is the algorithm for completing the square. So if I divide both of these by 3, I'll end up with 3 times x squared plus 18x divided by 3 is 6x. Then what I'm going to do is take the coefficient of x that's inside the bracket. So I'm going to take 6. And I'm going to turn this bracket into a perfect square trinomial. And remember, the way to do that is to take this number, divide it by 2, and then square it. This is the number I need at the end. Now, unfortunately, if I just add 9 here, that'll change the value of the equation. That'll make the right side different than the left side. So not only do I have to add 9, I have to add and subtract it. And now I've basically added 0. And so I haven't changed the value of the expression at all. The problem is, while this is a perfect square trinomial, this kind of messes that up. So I'm going to remove the negative version from inside the brackets. But if I do that, remember I have this many of this. So I have to multiply it by my a value, which in this case, of course, is 3. And that'll move it outside the brackets. And now my rewritten expression will be y equals 3 times x squared plus 6x plus 9. And this is a complete perfect square. This negative 9, if I multiply by 3, I get negative 27, and I put that outside the brackets. And now that I have a perfect square trinomial, I can actually factor it. And it will always factor into x plus b over 2a, or half of this number right here, right? We've already divided it by a. We can divide it by 2 as well to find its new value, all squared. So this will always factor into x plus b over 2a squared. And at the same time, I can also collect the like terms on the outside here. And so my new expression is y equals 3 times x plus 3. It's always going to be half of this number, x plus 3 squared. And 18 minus 27, of course, is negative 9. That is my exact same quadratic relation, except instead of standard form, it's in vertex form. And using this, I can very easily identify that the vertex is at negative 3 and negative 9. Now, because of this algorithm, because this number is always going to be half of this, and this number is always b divided by a, I can always find the x value of the vertex, even from standard form, just by taking negative b over 2a. Right? B divided by a, and then over here I'll divide it by 2, just because like we saw in that perfect square, I had to move half of the x tiles to the length and half to the width. So this is half of this, so b divided by 2a. But because this is x plus b over 2a, and the vertex form is x minus h, I would then have to change that to negative. So the x value of the vertex is always going to be negative b over 2a. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.